Hello everyone. I'm continuing on in this video where we were covering this paper on prompt learning, this survey paper, and sorry, prompting. And we had finished up to the fifth section, and the fifth section talked about creating your answers. So I believe it was titled Answer Engineering. Yeah, Answer Engineering. So now we'll move on to the sixth section, which is multi-prompt learning. Alright. So the prompt engineering methods we discussed so far focus mainly on constructing a single prompt for an input. However, a significant body of research has demonstrated that the use of multiple prompts can further improve the efficacy of prompting methods. And we will call these methods multi-prompt learning methods. So in practice, there are several ways to extend the single prompt learning to multi-prompt, and they'll summarize all of them. So first of all, you have prompt ensembling. So prompt ensembling is a process of using multiple unanswered prompts for an input at inference time to make predictions. So an example is figure 4a. So you have these prompts: China's capital is dash is the capital of China, and the capital of China is dash, and then you combine all of them and give that as input. So this sort of prompt ensembling can leverage the complementary advantages of different prompts, alleviate the cost of prompt engineering since choosing one best performing prompt is challenging, it varies from case to case, and stabilize performance on downstream tasks. Because some prompt might work better than the other in some cases and so on, but on an average, they'll hopefully be stable. Prompt ensembling is connected to ensembling methods that are used to combine together multiple systems which have a long history in machine learning, so of course random forests and so on. Current research also borrows ideas from these works to derive effective ways from prompt ensembling as described below. So you have uniform averaging. The most intuitive way to combine the predictions when using multiple prompts is to take average of probabilities from different prompts. So concretely, this indicates that you're just averaging over the probability of the tokens, where this is the prompt for the ith prompt. This is the function for the ith prompt. Jiang et al. First filtered these prompts by selecting k prompts that achieve the highest accuracy in the training set, and then use the average log probabilities obtained from the top k prompts to calculate the probability of for a single token at z. So this is like uh, each prompt would give a probability distribution at z for tokens, and then they can just uniformly average that. So this was when performing factual probing tasks. There you can have a single answer. Schick and Schurz also try a simple average when using ensemble method to annotate an unlabeled dataset. When performing text generation, Yuan et al. Formulate the task as a text generation problem and take average of the final generation scores obtained using different prompts. So you can just see how this is happening. So suppose this gives a distribution of uh, Beijing with probability point 2, Shanghai with probability point 1, and so on. Then here also you'll get a similar distribution. Let's say this prompt failed and it said Delhi with a probability of point 0.3, which is the capital of India and not China. And then Beijing is the second one with say probability point 0.1. But the third one again gave a similar distribution as the first one, but having different probabilities. On an average, when you average up these probability distributions over the tokens, Beijing would hopefully be the best answer, or the answer with the highest probability mass. Then you have weighted averaging. So instead of simple averaging, you can also in the case of simple averaging, you are giving equal weightage to every prompt, but some prompts might be better than others. So to account for this, you can have a weighted average for prompt ensembling, where each prompt is associated with a weight. The weights are typically pre-specified based on prompt performance or optimized using a training set. For example, Jiang et al. Learn the weight for each prompt by maximizing the probability of a target output over training data. Kin and Eisner 2021 use the same approach except that the weight for each prompt is optimized together with soft prompt parameters. Besides, Kin and Eisner 2021 also introduced a data-dependent weighting strategy where the probability of the input appearing in that prompt is also considered in the weighting of different prompts. So uh, the probability, I guess this is just learned from the training set. So if the prompt occurs in the training data, then is the input likely to occur in that, and so in the placeholder place and so on. She can shows 2021 A and B set the weight for each prompt proportional to the accuracy in the training set before training. So this seems like a more intuitive way. So the first and the third way. The second one also looks pretty ingenious, if I must say. But all of these like make a lot of sense. Then you have majority voting. For classification tasks, majority voting can also be used. So the highest probability mass. So I guess you are just using, instead of averaging over the probability, you're just taking the one which has the highest absolute probability across all distributions. That could be one way. Then you have knowledge distillation. An ensemble of deep learning models can typically improve the performance, and this superior performance can be distilled into a single model using knowledge distillation. So to incorporate this idea, Schick and Schultz train a separate model for each manually created template answer pair and use the ensemble of them to annotate an unlabeled dataset. Then the final model is trained to distill the knowledge from the annotated dataset. Gao et al. 2021 uses similar ensemble method on their automatically generated templates. So what they're trying to do is they're trying to extract knowledge from an ensemble of deep learning models, so multiple deep learning models. To do this, they create some pairs, and they get it annotated by the ensemble, and the final model learns on that annotated dataset, so it gets knowledge from all the models, hopefully. Again, there are no guarantees, but there are no guarantees anywhere in deep learning. Then you have prompt ensembling for text generation. So there's relatively little work on prompt ensembling for generation tasks, tasks where the answer is a string or token of string. A simple way to perform ensembling in this case is to use standard method that generate the output. Sorry about that. Based on the ensemble probability of the next word in the training sequence. In contrast, Schake and Schultz train a separate model for each prompt, and and thus storing each of these fine-tuned language models in memory is infeasible. Instead, they first decode generations using each model and then score each generation by averaging the generation probability across all models. So I guess they are just uh, okay. Let me just read that again. A simple way to perform ensembling in this case is to use standard methods that generate the output based on ensemble probability of the next word in the answer sequence. So the next token is you give the input prefix prompt or anything which you've decoded so far, and then all the models predict the next token, and the token with the highest probability is chosen, and then that is again fed by appending that to the input string to the next time step of decoding. Then you have prompt augmentation. Prompt augmentation, also called demonstration learning, provides a few additional answered prompts that can be used to demonstrate how the language model should provide the answer to the actual prompt instantiated with the input text. For example, instead of just providing a prompt of China's capital is Z, the prompt can be prefaced by example, Great Britain's capital is London, Japan's capital is Tokyo, China's capital is Z. So this would give the model more context about what they're looking for. Another example of performing addition of two numbers can be found in figure 4b. These few demonstrations take the advantage of the ability of strong language models to learn repetitive patterns. Although the idea of prompt augmentation is simple, there are several aspects that make it challenging. So, how do you select samples which are effective, and how do you order them? So, before that, let's just have a look at the example which they mentioned. So you show it two prompts. 1 plus 1 is 2, 2 plus 5 is 9, and then 6 plus 8 is mask, and then the model has to guess. But now the model at least knows, hopefully knows your intention. For sample selection, researchers have found that the choice of samples used in the few shot scenario can result in very different performance, ranging from near state of the art to near random guesses. To address this issue, Gao et al. And Liu et al. Utilize sentence embeddings to sample examples that are close to the input in embedding space. To measure the generalization capability of pre-trained language models to perform new tasks based on instruction, Mishra et al. Provide positive samples and negative samples that highlight things to avoid. So these are just some heuristics. Uh, so the first heuristic is taking examples whose embedding are closer in the embedding space, and the second method is giving both positive and negative samples. So the positive samples tell it what to do, and the negative samples tell it what not to do. For sample ordering, again, Liu et al. 2021 found order of answered prompts provided to the model play an important role in model performance and provide entropy-based methods to score different candidate permutations. Okay, Kumar Talukdar 2021 search for a good permutation of training examples as augmented prompts can learn a separated token between prompts for further gain in performance. So they just look for good permutation of training example as augmented prompts, and they have a special separator token which is also learned, which tells the model, okay, these are distinct prompts or distinct examples. Prompt augmentation is closely related to retrieval based methods that provide more textual context to the model to improve performance, a method that has been shown to be effective in prompt based learning. However, the key difference lies in the fact that prompt augmentation also leverages the template and answer, while the larger context learning does not. Again, so we're now on to the third one, which is prompt composition. For composable tasks which can be composed based on more fundamental subtasks, we can perform prompt composition using multiple subprompts, each for one subtask, and then defining a composite prompt based on those subprompts. So you take multiple subprompts for different subtasks and create a composite prompt for all of those tasks. This is only valid for composable tasks. For example, in the relation extraction task, which aims to extract the relation of two entities, we can break down the task into several subtasks, including identifying the characteristic of entities, classifying the relationship between entities, and so on. So based on this intuition, Han et al. First used multiple naturally created subprompts for entity recognition and relation classification, and then composed them into a complete prompt based on logic rules for relation extraction. So I guess this is pretty self-explanatory why prompt composition works. So let us now have a look at some example on prompt composition. For instance, Google became a subsidiary of Alphabet as the input. Then you have X the mask Google, X the mask Alphabet, X Google mask Alphabet. So these are sub prompts, and then you can combine them. So what this basically does is now the model uh, is doing multiple tasks which were composable before together. And this also gives the model more idea about, okay, maybe just having one token to fill does not give it enough context, but seeing, okay, I also need to fill those things, or the model probably doesn't know that it needs to fill those things, but it knows there is some context ahead as well, which can be used. Then you have prompt decomposition. So what tasks where multiple predictions should be performed for one sample, like sequence labeling. Directly defining a holistic prompt with regard to the entire input is challenging. One intuitive method to address this problem is to break down the holistic prompt into different subprompts and then answer each subprompt separately. So figure D shows this for NER, which aims to identify all entities in inputs. In this case, the input will first be converted into a set of text spans, and the model can then be prompted to predict the entity type. So like including not an entity for each span. It is not easy to predict all the span types at the same time due to large number of spans, so different prompts for each span can be created and predicted separately. This sort of prompt decomposition for named entity recognition has been explored by Suri et al. So again, going back to the example, you had this sentence, Mike went to New York yesterday, and then you create two prompts, X, Mike is mask entity type, and then New York is mask entity type. These are two prompts, and then you can create sub prompts from that. So I think this entire section on prompt augmentation is not prompt augmentation, multi-prompt learning is clear now? So this is a part of the broader, uh, like this is a section of the paper which is now completed. So now we'll be moving on training strategies for prompting methods. So far we've just seen how do we build prompts, right? How do we train the models when we have prompts? With the methods in the above section, it is now clear how to obtain an appropriate prompt and the corresponding answers as well. Now let's discuss about methods that explicitly train model in concert with prompting. So training settings. In many cases, prompting methods can be used without any explicit training of the language model for the downstream task. Simply take a language model trained to predict probability effects and applying it as is to fill the close or prefix prompts defined to specify the task. So this is what you call zero shot, where you do not tell it anything. However, there are also methods that use training data to train the model in concert with prompting methods. These either consist of again full data learning, where a reasonable large number of training examples are used to train the model, or few short learning, where a very small number of examples are used to train the model. Prompting methods are particularly useful in the latter case, as there are generally not enough training examples to fully specify the desired behavior, and thus using a prompt to push the model in the right direction is particularly effective. One thing to note is that many of these prompt engineering methods described in section 4, although annotated training samples are not explicitly used in the training of the downstream task model, they are often used in the construction or validation of the prompts that the downstream task will use, because you can't just create prompts, right? You also need to test how good they are. Something might seem very reasonable to a human, but it might just break down in front of a machine. This is arguably not true zero shot learning with respect to the downstream task, as you're again doing some sort of validation beforehand for your prompts. But who cares till it works, right? Although claiming it is zero shot might be wrong. Then you have parameter update methods. So far we were just seeing the training settings. So in prompt-based downstream task learning, there are usually two types of parameters, namely those for the pre-trained models and the prompts. Which part of parameter should be updated is one important design decision, which can lead to different levels of applicability. We summarize 5 tuning strategies based on whether the parameters of the underlying language model are tuned, whether there are additional prompt related parameters, if there are additional prompt related parameters, whether those parameters are tuned. So this basically just differentiates your uh, training methods into what all parts of the model are being trained. So is it just training the model, or is it also training the prompts? So for instance, you have promptless fine tuning, where the parameters are tuned. Then you have tuning free prompting, then fixed language model prompt tuning. So I guess they'll be discussed in detail below, right? So let's have a look at first promptless fine tuning. As mentioned in introduction, the pre-train and fine-tune strategy has been widely used in NLP since before the popularization of prompting methods. So pre-training and fine-tuning without prompts are called promptless fine-tuning, to contrast with the prompt-based learning methods introduced in the following section. In this strategy, given a dataset, all or some of it, of the parameters of the pre-trained language model will be updated via gradients induced from the downstream training samples. So, like sentiment classification. Typical examples are BORT and Robota. This is simple, powerful, and widely used method, but it may overfit or not learn stably on small data sets. Models are also prone to catastrophic forgetting, where the language model loses its ability to do things that it was able to do before fine-tuning. So advantages again, simplicity. There is no need for prompt design, because uh, you're not you're doing promptless, right? You have no prompts, and tuning all parameters, language model parameters allows the model to fit to larger data. So and the disadvantages are overfitting and no not stable training on smaller data sets. Then you have tuning free prompting. Tuning free prompting directly generates the answers without changing the parameters of the pre-trained language models based only on a prompt. These can be optionally augmenting inputs with answered prompts as described in section 6.2, and this combination of tuning free prompting and prompt augmentation is also referred to as in-context learning. All right. Typical examples of tuning free prompting include Llama and GPT-3. So Here you are just generating the answer without changing any of the language model parameters and only using the prompt. So similar to how people played around with GPT-3. So advantages, since there are no parameter updates, there is efficiency, there is no catastrophic forgetting, since the models are parameters are frozen, and it is applicable in zero shot settings. Disadvantages is because uh, prompts, the only task specific information are going in through the prompts, then you need to have very good prompts to achieve high accuracy. And in particular, in the in context learning setting, providing many answered prompts can be slow at test time and thus cannot be easily used uh, on large training data sets, because uh, if you have multiple many answered prompts, then you need to get them from somewhere, right? You need to process them. Fixed language model prompt tuning. So in this case, additional prompt relevant parameters are introduced based on besides the parameters of the pre-trained model. So fixed language model prompt tuning updates only the prompts parameter using the supervision signal update from the downstream training samples, while keeping the entire pre-trained language model unchanged. So here your language model remains unchanged, only your prompts are being tuned. So the examples of prefix tuning and warp. So advantages are similar to tuning free prompting. It can retain knowledge in language models since their parameters are not updated and is suitable in free few short scenarios. And of course, tuning it gives better accuracy than tuning free prompting in many cases. It is not applicable in zero shot scenarios. While effective in few short scenarios, representation power is limited in large data settings because you cannot use all of it. And then prompt engineering, though through choice of hyperparameters or seed prompts is necessary. And prompts are usually not human interpretable or manipulable because your prompts are like parameters that are updated. So you know what the initial prompt was, but after some updates you don't know. Then you have fixed prompt language model tuning. Fixed prompt language model tuning tunes the parameters of a language model, as in the standard pre-train and fine-tune paradigm, but additionally uses prompts with fixed parameters to specify the model behavior. So this potentially leads to improvements, particularly in few short scenarios. So here, it's like you have your pre-train and fine-tune paradigm. You are tuning the language model parameters, but you are keeping your prompts fixed. So the prompt parameters are not tuned. So the most natural way to do is to provide a discrete textual template that is applied to every training and test example. So you just add it your uh, your input into that template. Some example are PET-TC, PET-CHIN, and LMBFF. Logan 4 et al. 2021 more recently observed that prompt engineering can be reduced by allowing for a combination of answer engineering and partial language model fine-tuning. For example, they define a very simple template, null prompt, where the input and mask are directly concatenated without any template words, and find this achieves competitive accuracy. So your model is just learning to parse these prompts. So advantages: prompt or answer engineering more completely specify the task, allowing for more efficient learning, particularly in the case of few short scenarios. And disadvantage: prompt or answer engineering are still required, which is again expensive and difficult, although perhaps not as much as without prompting. Language models fine-tuned on one downstream task may not be effective on another one. So again, these are some of the disadvantages. Then finally, you have something which does everything, prompt plus language model tuning. In this setting, there are prompt element parameters which can be fine-tuned uh, together with all or some of the parameters of the pre-trained model. Representative examples include PADA p-tuning and p-tuning. Notably, this setting is very similar to standard pre-train and fine-tune, just having some additional prompt parameters. Advantages: this is the most expressive method because you have all of the world's parameters at your disposal to train. Disadvantages: it requires training and storing all parameters of the model, and it may overfit to smaller data sets. So I think this is pretty clear now. What are these five different tuning strategies? Again, if you go back to the table, promptless fine tuning, your language model parameters are already tuned. You are not doing anything. You're just asking the MLM to fill in words. Then you have tuning free prompting where nothing is tuned. Then you have fixed language model prompt tuning where your additional language model is fixed but your prompts are being tuned. Then you have fixed prompt language model tuning where your prompts are fixed but your language models are tuned. And then you have prompt plus language model fine tuning where both of them are tuned. So with this we finish section 7 and move on to section 8. So in previous sections, we examined prompting methods from the point of view of the mechanism of the method itself. In this section, we rather organize prompting methods from the point of view of which application they have been applied to. So where are they being used? So knowledge probing, factual probing. So factual probing or fact retrieval is one of the earliest scenarios with respect to which prompting methods were applied. The motivation of exploring this task is to quantify how much factual knowledge the pre-trained language model's internal representations bear. So in this task, the parameters of the pre-trained model are usually fixed and knowledge is retrieved by transforming the original input into a closed prompt, which can be manually crafted or automatically discovered. Relevant datasets including llama and X factor, including I guess it should be include, not including. Since the answers are predefined, fact retrieval only focuses on finding effective templates and analyzing the results of different models using these templates because your answers are fixed one words or few words, I guess. Both discrete template search and continuous template learning have been explored, as well as prompt ensembling. All right. For linguistic probing, besides factual knowledge, large-scale pre-trained learning also allows language model to handle linguistic phenomena such as analogies, negations, semantic role sensitivity, semantic similarity, cant understanding. I'm not really sure what that is, and rare word understanding. The above knowledge can be elicited by presenting linguistic probing tasks in the form of natural language sentences that are completed by the language model so you understand where does it fail or does it truly understand the linguistic phenomena. Then you have your classification based tasks. So prompt based learning has been widely explored in classification based tasks where the prompt templates can be constructed relatively easily, such as text classification and natural language inference (NLI). The key to prompting for classification tasks is reformulating it as an appropriate prompt. So you can use a prompt like the topic of this document is Z, which is then fed into a masked pre-trained language model for your slot filling. For text classification, most previous work has used closed prompts, and both prompt engineering and answer engineering have been explored extensively. Most existing works explore the efficacy of prompt learning for text classification in the context of few shot and fixed prompt language model tuning. Then you have natural language inference. It aims to predict the relationship, like entailment of two given sentences. Similar to text classification, for NLI tasks, closed prompts are commonly used. Regarding prompt engineering, researchers mainly focus on the template search in the few shot learning setting, and the answer space is manually pre-selected from the vocabulary. This is just a table of different model methods. So these are different prompting works. And let's just look at the column names, the tasks they're used on, the pre-trained language model uses setting, prompt engineering done or not, answer engineering done or not, tuning done or not. What's mul PR? I'm not entirely sure. What's the last column? Okay, so they have mul PR column list multiple prompt learning methods. So which of those? Okay, these are just abbreviations for that. For information extraction, unlike classification tasks where closed queries can be intuitively constructed, uh, these for these tasks it is much more difficult as you might guess. For relation extraction, uh, here you need to predict the relationship between entities in a sentence. Shen et al. First explored the application of fixed prompt language model tuning and discussed two major challenges that hinder the direct inheritance of prompting methodology. You have a larger label space like 80 relations versus true in sentiment classification, which results in more difficulty in answer engineering. And in relation extraction, different tokens in the input sentence may or may not be less important. So, like entity mentions are more likely to participate in a relation than, say, some adjective, which, however, can not be easily reflected in the prompt template for classification since the original prompt template regards each word equally. To address these problems, Shen et al. Propose an adaptive answer selection method to address the issue. Task-oriented prompt templates constructed for the issue, where they use special markers like E to highlight the entity mentioned in the template. So this gives the model more information about where the entities are. Han et al. 2021 incorporate entity type information via multiple prompt composition techniques. Then you have semantic parsing. Semantic parsing is a task of generating structured meaning representation given a natural language input. Shen et al. 2021 explored the task of few short semantic parsing using language models by framing the semantic parsing task as a paraphrasing task, constraining the decoding process by only allowing the output valid according to the grammar. So this allows you to do semantic parsing by having these additional layers involved. They experiment with the in-context learning setting, choosing answered prompts that are semantically close to the given test example, determined by the conditional generation probabilities of generating a test sample given another training sample. The result demonstrates the effectiveness of paraphrasing reformulation for semantic parsing tasks using pre-trained language model. So again, what is semantic parsing? It is generating the structured meaning representation given an input, and for this, uh, you need the best results were obtained by framing the semantic parsing task as a paraphrasing task where you ask the model to paraphrase it, and then you constrain the decoding process by only allowing valid output valid according to a grammar which you have. Then for NER, the task is identifying named entities. The difficulty of prompt-based learning application to tagging tasks is exemplified as NER because each unit to be purchased a token of span. There is a latent relationship between the token label, and overall the application of prompt-based learning in tagging tasks has not been fully explored. So Sui et al. Recently proposed a templates-based NER model using BART, which enumerates text spans and considers the generation probability of each type within manually crafted templates. So for example, you have this Mike went to New York yesterday. To determine what type of entity Mike is, they use a template Mike is a Z entity, and the answer space Z consists of values such as person and organization. Then you have reasoning in NLP. There's a debate about if deep neural networks are capable of performing reasoning or they are just memorizing patterns. So there have been a number of attempts to probe language models' reasoning ability by defining benchmark tasks that span different scenarios, and some of them are discussed here. So after this, I guess we have a couple of more applications and some resources, and I'll probably end there. And these last few sections, uh, I'll cover them in a final video on this topic. Alright, so for common sense reasoning, there are a number of benchmark datasets testing common sense reasoning. Some commonly ones are Vinograd schemas, which require the model to identify the antecedents of an ambiguous prompt within the context or involve completing a sentence given multiple choices. For the former, an example could be the trophy doesn't fit into the brown suitcase because it's too large, and the task for the model is to infer whether it refers to the trophy or the suitcase. So this is just common sense which us humans can easily uh, re- figure out, right? So by replacing the word it with its potential candidates in the original sentence and calculating the probability of the different choices, pre-trained language models can perform quite well by choosing the choice that achieves the highest probability. For the latter, an example could be Eleanor offered to fix her visitor some coffee. Then she realized she didn't have a clean Z. And again, the candidate choices are cup, bowl, or spoon. The task for the pre-trained language model is to choose the one from the three candidates that most conforms to common sense. For these kinds of tasks, you can score the generation probability of each candidate and choose the one with the highest probability. So just look into your vocabulary post softmax, and then in the words which you're particularly interested in, see which one has the highest probability. So mathematical reasoning is the ability to solve mathematical problems like arithmetic addition, function evaluation. Within the context of pre-trained language model, researchers have found that pre-trained embeddings in language models can perform simple operations such as addition and subtraction when the number of digits is small. but fail when the dates are larger. Some works explore more complex mathematical functions like exponential and nested functions, a reasoning problem, and improve the language model performance to serializing functions for the operation. So you first tell it what is f of x, then you tell it you want f of 3. So as a human, I can see that would be 81, hopefully. So 3 into 3, 9, and then 9 into 9, 81. For Q&A, you have the task is to extract a given answer the question, often based on a context. Q&A can take a variety of forms. So you have extractive Q&A where you extract the answer, which is squad, multiple choice Q&A, like race and free form Q&A, where the model returns an arbitrary textual string as a response, like narrative Q&A. Generally, these different formats have been handled using different modeling frameworks. One benefit of solving Q&A problems with LMs, potentially using prompting methods, is that different formats of QA tasks can be solved within the same framework. So you don't need specific modeling frameworks. For example, Khashabi et al. Reformulate many QA tasks as just text generation problems by fine-tuning sequence-to-sequence based pre-trained models like T5 and appropriate prompt from the context and question. Jiang et al. Take a closer look at such prompt-based QA system using sequence-to-sequence pre-trained model like T5 bar GPT-2 and observe that the probabilities from these pre-trained models on QA tasks are not very predictive of whether the model is correct or not. I don't think GPT-2 is a sequence-to-sequence model. I think it's just, a, I guess it can be treated like one, but I'm not sure if it is truly one because it does not have an encoder like T5 and BART do. For text generation, you have it is a family of tasks that involve generating text, usually conditions some other piece of information. Prompting methods can be easily applied to these tasks by using prefix prompts together with autoregressive pre-trained language models. Radford et al. 2019 demonstrated impressive ability of such models to perform generation tasks such as text summarization and machine translation using prompts such as translate to French. Brown et al. Performed in-context learning for text generation, creating a prompt with manual template and augmenting the input with multiple answered prompts. Chicken Shoots 2020 explored the fixed prompt LM tuning for few short text summarization with manually crafted templates. Li and Liang 2021 investigate fixed language model prompt tuning for text summarization, data to text generation, few short setting where learnable prefix tokens are prepended to the input while parameters and pre-trained model are kept frozen. Dow et al. Explore the prompt plus language model tuning and text summarization, where learnable prefix prompts are used and initialized by different types of guidance signals, which can then be updated together with the parameters of the pre-trained language models. So if I seem like I'm going too fast, I am because this is not something which I can really explain. These are just works which have happened, and this is things which they have done. So I believe if we reach this part, you totally understand what all of this means. For automatic evaluation of text generation, Yuan et al. Have demonstrated that prompt learning can be used for automated evaluation. Specifically, they conceptualize the evaluation of generated text as a text generation problem model using a pre-trained sequence-to-sequence model, and then use prefix prompts that bring the evaluation task closer to pre-training tasks. They experimentally find that simply adding the phrase such as to the translated text when using pre-trained models can significantly cause improvement in German to English MT. For multimodal learning, Simpo Kelly et al. Shift the application of prompt learning from text-based NLP to multimodal setting. They specifically represent each image as a sequence of continuous embeddings, and a pre-trained language model whose parameters are frozen is prompted with the prefix to generate text to its image caption. Empirical results show few short learning ability with the help of a few demonstrations. Systems can rapidly learn words for new objects and novel visual categories. So this is now extending your models to more embedding spaces. For meta applications, you have domain adaptation. So practice of adapting a model from one domain like news to social media. And for this, you use self-generated DRS, which are domain-related features, to augment the original input. For debiasing, this is just self-diagnosing the issues in the model and debiasing based on some instructions. So you have, say, the input, the following text contains violence xz, then we fill x with input and then look at the generation probability at z. If the probability is yes or no, then we can know what it is. Then to perform debiasing, we first compute the probability of next word, then we compute the probability of next word by appending self-diagnosis textual input as mentioned. The two probability distributions can be combined to suppress the undesired attribute. For dataset construction, you can just use it to write two sentences that mean the same thing, and then you attempt to generate sentences that creates datasets in an automated fashion. And here are some resources for the same. So I'll be ending this video here. This is already around 40 minutes long, and I guess we'll have around one more video. Yeah, that I think should do it because a lot of the remaining paper is just tables and stuff, and that would finish us up for this paper. So thank you guys for tuning in. Hope to see you next time as well.